Okay, thank you.
So, good morning, everyone. I think we can start. And our first speaker this morning is Siye Gauge from Tsinghua University, Taiwan. And he will tell us about gauge theory, sigma models, and generalized geometry. Please.
Thank you very much. It's my great pleasure to have an opportunity to give a talk here. And I very much like to thank the organizers for carefully putting together this exciting conference. And I also enjoy my visit to Corfu, which is my first visit. So I will talk about some physical models of gauge theory and sigma models and the relation to generalized geometry. More specifically, the gauge theory in question is Kapustin-Witten theory. This is a twisted version of n equals to 4 gauge theory in 4 dimensions. And if we do a standard dimensional reduction, namely, if we assume our 4-dimensional spacetime is 2-dimension times a surface of which is very small, then effectively we have a 2-dimensional model. In this case, it's a sigma model whose target space is a hyperkähler manifold, which I will mention in more detail. And this, by doing so, they were able to explain the mathematical theory called the geometric Langren's program by using electric magnetic duality. So today we'll first start with a brief review of this setup, and then I will mainly talk about reductions from a 4-manifold, which is not a global product of 2 manifolds of 2 dimensions. In fact, the vibration is a bit tricky, and also the 4-manifold contains non-orientable surfaces, although the 4-manifold itself is still orientable. So let's start with a general remark of gauge theory in 4 dimensions. And we will always take our gauge group to be a connected, compact, simple Lie group. And there's a complete classification of the Lie algebra of these Lie groups. And for each such a Lie group, a gauge group, there are 2 finite abelian groups. One is the fundamental group of the Lie group, which is relevant to the universal cover of that Lie group. And also, there's another finite abelian group, which is the center of the Lie group. Now, let's assume we have a four-manifold which has a space-time splitting. So it's the timeline cross spatial three-manifold, and doing so, although we can treat path integral for an arbitrary closed four-manifold, which is not a product, but in order to do canonical quantization, we do need such kind of space-time splitting. And also, such a splitting will enable us to separate electricity and magnetism. If we have a four-manifold, which is sort of closed by itself without knowing which time direction is, then there's no separate notion of electricity and magnetism. Okay, so this is we are still looking at a general gauge theory in four dimension, where the space-time manifold is a product of timeline and a three-manifold. So let us look at some topological aspect. Now, suppose we have a non-contractible closed surface inside this three-manifold, our space. Now, each such surface carries a what is called a discrete magnetic flux, and this was essentially due to 't Hooft, although he considered this special setting where our closed surface is a two torus and the gauge group is a projective unitary group, which is SUN mod its center Zn. In that case, the fundamental group is Zn. Now, in this case, the discrete magnetic flux is an element in Zn. And in general, for each closed surface, we have a discrete magnetic flux, which is in the fundamental group of the gauge group. Now, again, this is a finite abelian group of which Zn is an example. Now, in general, a three-manifold may have several such non-contractible closed surfaces. So, in other words, for each such surface, there is a kind of discrete flux here in this fundamental group. And therefore, for the whole theory, a discrete magnetic flux is an element in the second cohomology of Y with coefficient in pi1 of G. So this topological quantity can be fixed in quantization because it doesn't concern with the time direction, unlike instanton numbers, etc. So as a result, our quantum Hilbert space is a direct sum of sectors that are labeled by these discrete magnetic flux. Now let's now look at discrete electric flux. Now this is slightly more complicated. Now suppose our three-manifold, which is our space, has a non-contractible loop. So in other words, pi1 of Y is non-trivial. Suppose there is a non-contractible loop. Then I claim that the gauge theory has a ZG symmetry. So recall that ZG is a finite abelian group, which is the center of the simple Lie group. So why this is a symmetry? I have to explain to you how this center can act on the field. Now, the most difficult part is how it acts on the gauge field. So this action is simply as follows. For every element in the center, now I want to define what the action is. So the action is simply by modifying the holonomy along this non-contractible loop by this central element. And because the central element, this Z is a central element, it so the commute with all other possible polynomials, and this can be done without changing the curvature of the field strength, in other words, of the gauge potential. So we know that the action is written down in terms of F mu nu, and therefore this preserves the action, and therefore it's a classical symmetry. Now, in a general three-manifold, it may have many such non-controllable loops, and therefore the symmetry group is for each group you have this central element, and therefore this is the symmetry group is the first cohomology of Y with coefficient in ZG. Now, this is not yet the discrete electric flux. So what is the discrete electric flux? Well, we believe that such a symmetry survives at a quantum level, which means after quantization, there is a unitary representation of this group on the quantum Hilbert space. And therefore, the quantum Hilbert space, again, decomposes into sectors, which are labeled by irreducible representation type of this group. So namely, this is in the Pontryagin dual of the symmetry group, which I explained earlier. So this is an abelian group. So for each abelian group, it has several representations, and each representation is labeled by a homomorphism from A to the U1 group. So that's the labeling of irreducible representations of A. And now our A is this first cohomology group. So it's labeled by this by elements in this Pontryagin dual group, which is also a finite abelian group. And each element here, which labels a sector of the Hilbert space, is called a discrete electric flux. So I'm saying that this is mostly a review of Kapustin and Witten. So in fact, this is a slight generalization because they considered mostly the universal covering group or the adjoint group, but it's not difficult to generalize to any simple Lie group which has both pi1 and the center being non-trivial. Okay, so this is the setup that we are doing. Now, the other concept is about duality. For any simple Lie group, which we now use as a gauge group, there is a long-length dual group discussed by mathematicians for the purpose of studying number theory and automorphic forms, but it was independently discovered by physicists Godard, Nuit, Olive, and they call this group magnetic group. So let's give, so I'm not going to state the definition, which you can sort of look into the literature, but I'm only going to give some examples. For SUN, the dual is PUN. For SO to N, the dual is spin. So these are the same type in terms of Lie algebra and also E8. The dual is E8. But for type B and C, they are exchanges. Okay, so these are the examples. Now, then there is a sort of mathematical fact, which comes from essentially Poincare duality of three-manifold and also some Lie group Lie algebra theory, that we have these natural isomorphisms. So what does this mean in terms of physics? Now we look at the left-hand side. So this is precisely when the gauge group is G. This is the set of discrete magnetic fluxes. And on the right-hand side, this is precisely when the gauge group is LG, the set of discrete electric fluxes. So now you see that when we exchange G to its dual, the discrete magnetic fluxes is exchanged to discrete electric fluxes. in the dual theory. And conversely, it's also the same. We have another isomorphism. Okay, so that makes the electric magnetic duality possible. So it's very essential that our space-time is 4-manifold. So our space is a 3-manifold. So we have this kind of very similar isomorphism to Poincare duality. So now we have talked about 4-dimensional gauge theory. Now let's look at dimensional reduction from 4D to 2D. So for this purpose, let's assume, so we don't need to assume a space-time splitting structure. Instead, we assume that our 4-manifold is a product, a global product of a large surface, which will turn out to be the world sheet, and then a small surface, which will be internal surface, which will be get rid of in the dimensional reduction. So as you all know, at low energies, field along the C direction, because it's very small, have to satisfy the energy minimizing condition. Otherwise, even the first excited energy is huge. So there are some equations along C to be satisfied. And although I didn't write down the Lagrangian in the 4-dimensional theory, it turns out that the equation along the 2-dimension to minimize the energy would be exactly these Hitchin equations, where A is a gauge field on C, and phi is an adjoint bosonic matter field on C, and the equation to minimize the energy along C is are these, where Fa is the field strength of A, dA is the covariant derivative. Star is the Hodge star, because I assume that these, especially C, is orientable. So yeah, okay, thank you. So yeah, there is something that is not precise. So phi should be a 1 form, which is adjoint valued. So star is still a 1 form. Yeah, thanks. And then everything makes sense, because this is a 2 form, and this is also the right-hand side is also a 2 form. Yeah, thanks. Okay, so then we have the space of solutions modulo gauge transformation, and that's the moduli space. And it turns out that this space is hyperkähler, namely it has 3 complex structures and 3 Kähler forms. But these are just mathematical results. But what is relevant in physics is that the low energy theory of the 4D Young-Mills, when you do dimensional reduction in this particular way, it reduces to a sigma model whose world sheet is sigma, and whose target space is this Hitchin moduli space, because when you have a global product, then for each point in the world sheet, you would have a copy of C, and on that C, the equation have to be satisfied. So you get a point here. So in other words, you have a map from sigma to this moduli space, and so we have a sigma model. So what kind of sigma model is? We will come back later. Now, in general, let's talk about sigma model in 2 dimensions. Now, the correct amount of supersymmetry that if we follow the n equals to 4 in 4 dimension is n equals to 2 in 2 dimension. And a sufficient condition to have that amount of supersymmetry is the target space is Kähler. Of course, our target space now is hyperkähler, but it has too many Kähler structures. So we would like to know which one is the correct one. On the other hand, the target, in order to have this amount of supersymmetry, the target space doesn't have to be Kähler. It can be more general. According to Gates or Rorschach, we have a more general setting of target where we also have this amount of supersymmetry. So the target space in the more general setting has a metric, and it has two complex structures and a B field and two affine connections satisfying these conditions. So namely, G is Hermitian with respect to complex structure. G and the complex structure are parallel along these connection, and the torsion, the most important part is torsion is totally antisymmetric, and the torsion is plus minus h, where h is the curvature of the B field. Okay, so in this setting, they established that the sigma model also have this amount of supersymmetry. So now let's go to generalized geometry, which is part of the title and also the title, part of the title of this workshop. So in order to, so how much time? Okay, so So let's, in order to explain what generalized geometry is, let's first recall what geometry is. According to Riemann, we now live in the three-dimensional Euclidean space, but this depends on our experience. It's not given mathematically. So according to Riemann, if we extend the length scale to a very large one or very small one, our experience is no longer sufficient. So it's a question to decide whether our three-dimensional Euclidean space is still valid in a very large length scale and in a very small length scale. And he said that this is not a question of mathematics, this is a question of physics. And moreover, this is the most fundamental of all physics questions. And therefore, he proposed a notion which we now call differential manifold, which locally looks like a Euclidean space, but globally is not. So locally, we have Euclidean coordinates. And then he said this is for future use in physics, and future astronomical observation will tell whether we live in a Euclidean space or not. So this was the idea of Riemann when he proposed the mathematical notion, which we now call differential manifold. Now, although Riemann acknowledged there's also a problem of going to very small length scale, he didn't give any concrete plan of how we modify our Euclidean structure in small length scale. Of course, in this conference, I saw attempts using non-commutative geometry, and generalized geometry is a very mild version of non-commutative geometry in the sense that it is our space or space-time is still a set of points which has very clear, locally very clear commutative coordinates. So it has n coordinates, which are real numbers, just as when the notion was proposed by Riemann centuries ago. But the modification to the usual geometry is that the notion of direction is modified. Direction is sort of infinitesimal variation from one point to another. So it doesn't modify, it doesn't change coordinate to some non-commutative object, but it changed the notion of direction. So let's replace the tangent space of the manifold by the tangent space plus the cotangent space. So the dimension is doubled. And then there's a new bracket, which is a Courant bracket. So this is the vector field that is a one form, and you write down the bracket, which you can sort of read from many introductory papers or books on generalized geometry, which I do not write down. But then the idea is that this has double the dimension, that we have to return to the original dimension. And this is done when we take an isotropic subspace. So here there is a natural pairing between the tangent and cotangent space. And if you take an isotropic subspace, of which Tm is an example, if you take an isotropic subspace, maximal isotropic subspace, I'm sorry. So it will be again n dimension, and then it is should be regarded as a replacement of the tangent space. So, and of course, the bracket is changed, and the notion of tangent vector is also changed. So generalized geometry doesn't make our coordinate non-commutative, but it changes the direction. It changes the notion of directions, namely tangent vectors. Okay, so so with this notion of generalized geometry, then the data which this has so many objects, so we want to sort of organize them in a in a simple way. And in fact, this is done in the framework of generalized geometry. So in fact, these sort of data, complex structure, connection, etc. in the previous slide is equivalent to having a generalized scalar structure on M. So this means a pair of commuting generalized complex structures. So a generalized complex structure is a complex structure on this space of double the dimension. And then there's also a positivity condition, because you don't want to lose the positivity of the original Riemannian metric. So in this for the purpose of organizing this data, the generalized the two generalized complex structures are denoted by curly J, which are expressed in this expression, and they act on this space of dimension 2n, and the square is -1, and so this is these are complex structures, and you can check that they commute, and if you combine them in a suitable way, you have a sort of positive object, which is sort of replacement of positivity of the Kähler metric. Now, when the B field is equal to 0, and when J plus is equal to J minus, you return to the original notion of Kähler standard Kähler manifold. Okay, so now I have finished explaining all the sort of possible sigma models in 2 dimensions that we know of that could have this amount of supersymmetry. So now I have to be more specific. So for this particular 4-dimensional gauge theory, it will reduce to one of those sigma models that I mentioned. So what is it precisely? Okay, so we are back to our original gauge theory with this complex coupling parameter, and it turns out that after this particular twisting, there are 2 supersymmetries that survive on our curved 4 manifold. So if we twist an n equal to 2 gauge theory, like for the purpose of Donaldson theory, then there's only 1 supersymmetry, but now there are 2. And therefore, we can choose our BRST to be a topological sort of generator, to be a linear combination of those. And of course, only one of the coefficient matters. So I can take this to be a complex number or infinity. So T is an element in CP1. So there are CP1 worth of possible topological gauge theories. And for each T, now I reduce to a 2-dimensional sigma model, and I have described so many sigma models, and now I have to explain which particular one. And this particular one is that for each T, I have one of the I have a generalized complex generalized scalar structure on the Hitching moduli space, which is itself hyperkähler, but I'm not using one of those complex Kähler structures. In fact, the generalized Kähler structure, or one of the generalized complex structure, is written in this particular way. So everything is specific, where if I recall, I, J, K are the 3 complex structures on the Kähler target, and omega I, omega J, and omega K are the corresponding Kähler forms. Okay, so I write down this generalized complex structure using the hyperkähler structure on this target, and it's only this that is used. So in particular, when T takes this parameter, the theory is a B model with complex structure J. And if T is real or infinity, this is an A model, which is whose based on a synthetic form, which is a linear combination of omega I and omega K. And for other T, it's again related to A model in a simple way. Okay, so maybe now let's perhaps it's time that we compare the discrete fluxes in 4-dimension to 2-dimensional theory. Now, for this purpose, let's suppose our sigma worldsheet is a torus, and therefore the 4-manifold is a time direction across y, and y is this particular 3-manifold, and this discrete magnetic fluxes is in the second cohomology of y, which has this particular combination. So the discrete magnetic fluxes also decomposes. And this one says in which connected component of the Hitching moduli space do these closed string propagate. And this M1 is about winding number, because this space is not concretable. And what about discrete electric flux? It is here where Y is our 3-manifold. It also decomposes. And this part is because that the Hitching moduli space has a group action of this. So our sigma model has this symmetry, and therefore Hilbert space is decomposed into representations of this group, which are labeled by the Pontryagin dual. And here we have another element here, which gives the B field on the target space, which can also be incorporated topologically in the sigma model. Okay, so now we come to the point where I really want to discuss. So now in this sort of a variant of a Kapustin-Witten theory, our 4-manifold is still orientable, smooth, without boundary, but it contains some non-orientable surfaces, and it's not a global product. So how do we sort of construct such a 4-manifold? So once we have constructed that, then we can discuss our 4-dimensional gauge theory on this particular 4-manifold. Okay, so a non-orientable surface has an orientation double cover with a sort of Z2 action here on the total space. And we also assume that we start with orientable worldsheet, which has a sort of orientation reversing sort of map, which has fixed point. And therefore, if you take the quotient, you have a worldsheet with boundary, where the interior is sort of coming from the original worldsheet that are not fixed point, but the boundary comes from the fixed point. Okay, so then using this sigma tilde and C, we construct a 4-manifold, which is a product, but then you take the diagonal sort of action of the Z2. So this is a smooth manifold without boundary, and this is orientable because this reverses orientation of both vectors, and it preserves the orientation, and therefore the orientation survives on this 4-manifold. Okay, so let's look at gauge theory here, or look at gauge theory on this particular 4-manifold. And in order to do dimensional reduction, because this is not a global product, so we have to be more careful. Even though it's not a global product, there's a sort of projection map by forgetting the point in C, and therefore for each point on the worldsheet now with boundary, what is on top of that point is a copy of C if the point is in the interior, and it's a non-orientable surface if it is on the boundary. So in the limit when the worldsheet is large and when the interior sort of the extra 2 dimensions are small, then we have a low dimensional effective theory, which is again a sigma model. Now on the worldsheet without boundary, it is mapped to Hitching modular space, but on the boundary, because what is on top of the boundary is a non-orientable surface, so it is mapped on the boundary, it's mapped to Hitching modular space on the non-orientable surface. Now let's recall Hitching equation has a Hodge star, which depend on the orientation, but if it's non-orientable, the Hodge star has a sign ambiguity, but it doesn't matter because the right-hand side is 0. So this space still makes sense. So now we have a bulk theory, which is the same as the original theory, but the boundary lives on this particular brane, which is described here. So let's look at this target space, and the modular space for a non-orientable surface is mapped into the modular space for orientable surface. It is sort of simply by pullback of this double covering map, and this image is a B brane with respect to J, and it's the A brane with respect to omega I and omega K. And this is just right because for certain particular values, we do have a B model, which so the branes are sort of correct here. Now this sort of map is a finite cover with the group, which is the 2 torsion part of the center of the Lie group. Right. So now we explain the boundary condition. The boundary condition can also be explained in terms of generalized geometry. So let's recall that this is part of the modular space for an orientable surface. In fact, if you compute the generalized tangent bundle, it is this, and this is preserved by these generalized complex structures that form a generalized Taylor structure. So in that sense, this sort of trajectory sort of n is a generalized complex submanifold of the total space, and you can then conclude that if you put this kind of brane as boundary condition, that is, then it is consistent with the existing supersymmetry. So even if the bulk theory has this amount of supersymmetry, if you put the wrong boundary condition, it may no longer have that kind of supersymmetry. But fortunately, this is not the case. Okay, so then the last thing is that we should compare discrete magnetic and electric charges in 4 dimensions for this particular 4 manifold, and compare that with the 2-dimensional effective theory, which is now a sigma model with boundary living on branes, which I described in the previous slide. So for this purpose, let's assume that our 4 manifold has a T1 is a circle in the time direction, so it has a space-time splitting, and our 3 manifold is this Z2 sort of reflect the circle from the upper circle to the lower circle, so it has 2 boundary points, and then our worldsheet has 2 boundary, which is 2 boundary components which are circle. Okay, so for this particular 3 manifold, it's now exercise in topology to calculate the second cohomology, and it turns out that it has 2 parts. One part now we can explain in terms of 2-dimensional theory. So this is sort of the relative fundamental group of MH, relative to n because your open string has to end on this n. So what is relevant is the relative fundamental group, and this is precisely this if you look at the geometry of the modular space. And the other is now we have sort of a new modular space of non-orientable surface, and it has connected component, which are precisely this. And because open string has two ends, so we have two copy. So this everything that calculates topologically from 4 dimension has a two-dimensional matching. What about the discrete electric flux? Now, if you calculate the first cohomology with that particular y, it has also two parts. One is this, which is part of the symmetry on the Hitching moduli space, but only those that preserve the sort of the world volume of the brane, which is very natural. And the other is the deck transformation of this finite cover, which I talked about. But again, remember there are two boundary points for the open string, and so there are two copies, and this is sort of exactly what happens when you calculate from 4 dimensions. Now, the last thing I want to say is that in 4 dimension, there are two additional quantities in the discrete electric, magnetic, and electric flux. One is labeling the connected component of the modular space for orientable surface. Now, it turns out when we have brane, only this 0th component can support such kind of brane. So again, it's very natural that M0 doesn't show up in this topological calculation from 4 dimension. And the other thing is that E0 also doesn't show up anywhere here. It also has a reason in 2 dimension, because when E0 is non-zero, the 2-dimensional theory is anomalous. So anomalies throw out the possibility of non-zero E0. Okay, so I'd like to thank you for your attention, and so it's again, yeah.
Thank you very much for this nice talk. Yes, so time for some questions.
The very beginning,
yeah,
you had a reduction.
Yeah.
At the beginning, you or in general through the seminar, you use this reduction technique to the a little bit later to the world here, for example, for reduction to the world sheet.
Yeah.
Can you use it for a regular Kaluza-Klein theory with modes, without going through strings? Just go from, say, 6 dimensions to 4 dimensions or something. Of course, forms will have a different number of degrees and things.
Okay, so first of all, this is not string theory. This is still quantum field theory. String is just because our world sheet is 2-dimensional, and when it is a torus, or very much like a torus, it looks like a string propagation. But there's no notion of integrating over the moduli of this world sheet. So it's not a string theory. So in fact, I'm taking a particular 4-manifold and I fix that. So everything is fixed. Now, whether this is Kaluza-Klein or not, in Kaluza-Klein theory, we also have sort of maybe, so this is, suppose this is 5-dimensional, this is 4-dimension, this is 1-dimension, and I think this is the same kind of idea, except we have different fields. So here, where do the scalar sort of one-form field phi come from? It comes from the components of the gauge field in the C2 direction, whereas the component of the gauge field in the world sheet direction continue to become gauge field in the low energy theory. But because sort of in these two directions, we have trivialized things, so they become sort scalar, more like a scalar field. So this is very much like Kaluza-Klein theory, except that the fields are somewhat, maybe there are more fields because I have omitted the fermions.
Okay, more questions?
Yeah.
You described this generalized geometry.
Yeah.
And you say this is a different approach to, or similar to non-commutative geometry in a sense.
No,
yeah. What is the similarity, or what is quantum geometrical about generalized geometry?
Okay, so first of all, I didn't introduce fully generalized geometry.
Yes.
I just mentioned it. So generalized geometry turned out to be most useful if there is a B field around, as I said, it sort of modifies the notion of tangent vectors without modifying points. So this there's I don't have a precise sort of mapping between generalized geometry and non-commutative geometry that other people are talking about, although I believe that could be somewhat possible.
So let me maybe reformulate my question.
Yeah.
What do I win by doing generalized geometry? So
Sorry?
what advantage does generalized geometry have? So, or what do I win by doubling the tangent space?
Oh,
What do I gain from that?
So eventually you have to sort of reduce this doubled dimension.
Yes.
So now you replace your original tangent space by a subspace of this space of double the dimension. And then you regard that new space here, which is of correct dimension, as your tangent space. So when you now study sort of tangent vectors that infinitesimally move one point to the next, you should use this new subspace. And they have a new bracket. And that's why you have something new. So what you gain from that is a lot of things that are very messy to explain, like these become sort of very nicely organized.
And yeah, this in the back.
So you have split your entire manifold into a large part and a small part,
Yeah.
right? Yeah. And it's in the small part that you are using generalized geometry. Is that
No,
right?
it's not the small part, because the small part is C, which is a two-dimensional surface, which is still standard geometry. What is generalized geometry is the low energy, the target space of the low energy sigma model. The target space is Hitchings moduli space. It's hyperkähler, and therefore there could be many possibilities of generalized Kähler structure.
So is the fact that part of your space is small important for using generalized geometry, or you could use it even if both parts were of equal size?
If this is a physical theory, then you do need, in the dimensional reduction, you do need the fiber to be small. But since this is topological, probably the metric doesn't matter, but we can still think of that of small c. But what is important is that C is still a standard surface in the sense of usual mathematics, but the target space had better be viewed as a generalized space in generalized geometry. That will make the statement of many results simple.
So if I do want to think about this as a physical theory, then the internal space should be smaller than the real space, right? So
Right.
that would give us a scale at which the mixing between tangent and cotangent space will become relevant.
Yeah.
Right.
Yeah.
Can we? Is it sort of? Is there a way to see that as obvious? The scale at which this is a good idea, and then
well, the C, I'm sorry. The C, which is small, is part of the sort of parameter in defining this target space. Although I said this is not string theory because sigma is fixed, but if you use the string theory analogy, so this is map sigma to this target space. So if it were a string theory, it would be describing string on this space, which is now generalized geometry.
Thank you.
Okay, so I see no further questions. So let's thank the speaker again. Okay, so it's a pleasure to introduce our next speaker, Thomas Strobl from the University of Lyon. And unfortunately, the title is not printed in the version which I have here. So maybe you can announce your title yourself.
Okay, with pleasure. In fact, the title is a good point. So I was probably placed as a speaker after the previous one because I could have used precisely your title, but with a completely different angle, which is like the gauging of two-dimensional sigma models, giving a two-dimensional bosonic sigma model. If you want to gauge it, it turns out even in the more modern versions of gauging, there's always generalized geometry in the game, and what you call these isotropic subspaces, Dirac structures. But I have been talking about this since the early 2000s, so I wanted to say something newer and in a different spirit, and it's about angular momenta. Not bad. Angular momenta as constraints and a cohomological resolution of this the so-called BFV approach. And so let's and this will lead to some rather amusing structure. Namely, it turns out that one needs an infinite tower of ghosts and ghosts for ghosts for this very simple, supposedly very simple model. And to our surprise, we found a very nice structure in these ghosts. Namely, they come in the form of trees. So I'm trying to explain this a bit, and I start with an introduction where we maybe use also some notions of Lie algebroids a bit. But if you don't know it, then you can just forget this part, and afterwards everything should be very simple because I'm talking about trees. Okay, so the introduction first. So angular momentum, I just recall it was epsilon I jk x j dk. And what we want is we want to use them as first class constraints. So this lives in R6 with coordinates x and t. And they form the usual algebra. with the epsilon tensor as a structure constant, or maybe minus epsilon tensor, my conventions. So we want with Dirac notation put it to 0. And what is the problem with this? If you think a bit, this surface in R6, what does it say? It says that if I have the vector x non-zero, then the vector p should be parallel to it. But the moment x is 0, the vector p can be anything. So you see that it's not a smooth manifold. This is a kind of a subspace, which is not a manifold, in fact. And then a very similar strategy as in non-commutative geometry has to be applied, namely that one describes this algebraically. And so, and in this case, so let me first say what one wants. So one has, in principle, in the smooth setting, you have a symplectic manifold M omega. Maybe I should use some colors. You have some submanifold C inside, which corresponds to these constraints. And you have the flow of the Hamiltonian vector field of the constraints, which gives gauge symmetries. And in a very favorable case, this projects to a reduced phase space where our physics live. So each line here becomes one point here. Okay, but this carries a natural symplectic structure. This is called the Marsden-Weinstein reduction. And that works if everything is smooth. This is a smooth manifold. And also the leaf space here is smooth. So it's a very rare situation in the general. In particular, it's not satisfied for this case. And since already in physics, even if this is well defined and smooth, surface is difficult to describe. Thank you. Yes, so there's a cohomological approach to describe this, and it's called the BFV approach. And this works as such that one finds on a graded manifold where we have our ghosts and anti-ghosts. We find which also carries a BV bracket. We find a BFV charge, the function on this space, which satisfies the master equation, so that its Hamiltonian vector field defines a differential. This should be 0. And if you have given a Hamiltonian, so Hamiltonian must be a function which is also invariant under these flows, the gauge transformations, then also this needs to be extended to a function HBFV, which is the gauge invariance of this is represented by the fact that also this has to be 0. And the whole idea relies on the fact that the cohomology of this Q, this needs to first be unpacked, like in Christmas. So the cohomology of, let's call Q just the Hamiltonian vector field of this QBFV with respect to this bracket. Okay, I will drop this BFV if possible. So HQ at degree 0 should be isomorphic to the functions on a reduced phase space. So if it exists, so if it's non-smooth, then this should be the replacement of this. Now, what doesn't find in the case of angular momenta? Here, as in every algebraic setting, one needs to first say what are my functions on phase space. I will consider two different ones, either polynomials or C infinity functions. So let's call them O. Either polynomials in the variables x1, x2, x3, p1, p2, p3, or O can be also C infinity of R6. But I will mainly focus on this one now. And if one does, the algebraic description of this is you take this, for example, the polynomials, and you look at the ideal generated in the polynomials or in your O, in any case, by Li. So you get an ideal, you quotient by this ideal. This would be actually describing functions on the C, but you want to also quotient by this, and therefore you need to look at the Poisson normalizer of this ideal. So that is functions which, if you activate an element of the ideal, you stay inside the ideal. Okay, so that is what Dirac observables are called. And so this would be n of I over I, where I is this ideal generated by the angular momenta. And this would be the reduction. So, so what one wants is this. One can prove that this is always a Poisson algebra. It doesn't come from a manifold, but it's always a Poisson algebra in generalization of this symplectic form on the reduced space. This is always a Poisson algebra. So we want this even as Poisson algebras to be the same. And if I have Hamiltonian, for example, I have H being a half p vector squared plus a function of x vector squared or the radius, whatever, x vector squared. Then I also should get here the class in here should correspond to some class because n of I, the Hamiltonian lives in n of I. That's one of the definition of being Dirac observable, but then modulo I gives a class, and this isomorphism should also respect that. Okay, what is it in our case? If you calculate the reduction here, for example, in the polynomial setting, one can describe it as follows. So this is for our angular momentum. So one can look at polynomials on SO21 star. So polynomials I can describe as symmetric powers of SO21. SO21 star is a Poisson manifold, so there's a bracket, but you can also just think of it as the Lie bracket, and you extend the Lie bracket to polynomials by the Leibniz rule. And that would be like a three-dimensional space, SO21, so that's not what it should be. It should be two-dimensional. So we need to quotient by the ideal generated by the quadratic Casimir. So the quadratic Casimir in SO21 is just given by the 2-1 Lorentz metric. So essentially, you're saying that this space is the light cone in R3. Okay, so that's a singular space, and that is what one finds if one does this reduction in this case. That's the question? Right, right. This is surprising. It's and it works in each dimension, so this works for any dimension. So if you take a T star Rn with n at least 2, I think, then yeah, then you find always SL2R, SL21. And you find always this light cone SL1. It's not so complicated to find. You see, you look rotation invariant functions is x vector squared, p vector squared, and the inner product of x with p, and you calculate the Poisson brackets, and they just satisfy this algebra. Okay, but then you still have a kernel, so you need to quotient out something, and this reduces. So SO21 star. Dual of SO21 is a Poisson manifold. There's symplectic leaves. One of the symplectic leaves are the parts of the light cone, and actually the complete light cone in this setting is the reduction here, okay, which now is described purely algebraically. This has a Poisson bracket and so on, because the Casimir lives in the center of this Lie bracket. So this is the Poisson algebra one wants to find. Okay, now there are two naive approaches. One of which I learned when I was like a PhD student, like Sergei Shabanov explained it to me. So he had a lot of toy models for understanding the Gribov problem, and one of those was such this system, and they always used QBFV being the obvious thing. So you have some ghosts, eta I times the constraints Li. And then you have the usual term like plus a half or minus a half structure constants, which is here epsilon I jk. Then you have a term quadratic in the ghosts and the anti-ghost or ghost momenta. So and HBFV in this case, let H be just for the part now, I take H equal to the free Hamiltonian, is just the free Hamiltonian, then there's no extension needed because you see that here this is rotation invariant, so it's Poisson commutative here, and this doesn't depend on x's and p's, right? So they satisfy these two conditions in a very obvious way, but it doesn't satisfy this condition. Even if you exclude the origin, you can show that you get too much, okay? And the reason is that you didn't take into account the ghosts for ghosts, so the ghosts are somehow too many, and one needs to correct this. So, in this context, HQ0 is too big. Now there's a reformulation of this setting, which now uses some Lie algebroids, which I don't want to introduce, but if you don't know it, you just get some idea maybe. So you may introduce a vector bundle to be SO3 times R3 over R3. And here are your Lie algebra elements acting on this. So there's this map corresponds to some map rho to TR3, which is called the anchor map, and that's a Lie algebroid. In fact, the action Lie algebroid. And there's a description of Weintraub to describe Lie algebroids as graded manifold. So if my graded manifold is curly M, in this case, curly M would be E shifted by 1, which just means that the base carries even, it should be R6, by the way, sorry. We have X's and P's. No, it should be R3. Sorry, I'm mixing up things. So yeah, there could be also the action Lie algebra for R6, but I should now look at this one on the axis only, where you get coordinates xi I1, 2, 3 as before, and the fiber coordinates are odd. So these are degree 0, these have degree 1, and there's a vector field squaring the 0, which is equivalent to saying that this vector bundle has a Lie algebraic structure. So there's a Q which is epsilon I j k, so eta I epsilon I j k x j d by d x k plus a half epsilon I j k, not psi, I use eta here, eta I eta j d by d pi d by d psi eta. Okay, and q squared to 0 is the same as E is a Lie algebroid. And now there's a simple idea. You actually, this is not the same. That is M0. You take the cotangent bundle of this M0 and you put it equal to M, this curly M. So you get, for the axis, you get momenta, but also for the eta, you get momenta of the opposite degree. And then a vector field has a natural Hamiltonian lift. You just replace this by the corresponding momenta, and you see you just get this one. Okay, if you do this. So from this, you can go directly here by this kind of simple construction. And this gave us the idea to look at a different approach, namely this Lie algebroid, which describes a singular foliation on R3, can have a resolution in the context of sections, where here you have a line bundle 0, which corresponds to the condition that x, so this composition of the two maps is 0, so that xi epsilon I j k xj d by d xk is equal to 0. So we have this condition. And there is a Lie2 algebroid on this. So there's degree 1 coordinates, but also 1 degree 2 coordinate. This can again be described by some vector field squaring to 0. And you can take the Hamiltonian lift. It gives one extra term here. So it gives QB of V as above. Minus eta xi pi I, or xk pi k. Okay, so where this eta is a degree 2 variable. Actually, it turns out that the cohomology is still not good enough. One reason is that you see these LIs, they have this the redundancy that the inner product with x is 0, but also the inner product with p is 0. Actually, there are two redundancies, and you don't see it on the space of vector fields. So that's one thing that goes wrong, but there's something else which is even worse. For this classical Hamiltonian, one can prove there doesn't exist a BFV extension here. So there's cohomological obstruction, which we found with my student Sasha Hancharuk, and one can prove that doesn't exist. So how much time is for the free Hamiltonian doesn't exist. Okay, so now I want to explain you in the second part the construction that we find to get the right BFV charge, where we can prove then that this holds true. Okay, and for this purpose, I will restart from 0 and ask the question: what are trees with decorated leaves to your mind. So you have a tree and you have decorations on the leaves. Some balls here. And so on. So how would you call such a tree? Yes. So that's evidently a Christmas tree. So, right? So if you have a tree with decorated leaves, that's a Christmas tree. And the claim will be that these ghosts, eta, I, eta, but all the others we need, they actually in bijection to such Christmas trees, which I will explain to you which ones. So what are the rules of the game? So we have some planar tree. See, like this, I don't know. And on each of the leaves, we can put one Christmas ball. So there are two colors of them. And one will be blue. And if I had yellow, I would use yellow, but I don't, so I use red. Two types of balls. And they are decorated. So actually, these balls will carry an I from 1 to 3, and they kind of say which of, let's suppose our angular momenta are the children, which of the 3 children is permitted to take that ball. And so we have, so let's look at this very stupid tree, only one tree with this ball I, and there are 3 of them, and we call them degree 1, all of them. And the fact that these are the balls which go to child I is that I have this kind of future map, so which says that this tree I is for the child Li. Okay. Then evidently, to have a good family, we also need parents. So we have mother and the father, which correspond to the 2 relations I mentioned before. They are of degree 2. And their destiny is to have kids. So, for example, the mother, black, has her kids, which are now represented by these trees. So this it will be an operator of degree -1, as you can see. But fathers and mothers see the children a bit different. So here is the female version, xi, times this as a sum over repeated indices understood, evidently, and delta of, maybe I don't know if I should use always these colors, but let's try to stick to it. The father always has his destiny to be the children, but now the male version. Okay. So these are the elements of degree 1 in our setting. These are the elements of degree 2. But now we can look at more complicated trees, and we will say that each vertex carries degree 1. Okay. So what do we have at degree 3? Because we don't have any other balls, we can have only a tree with 1 vertex and 2 children, right? It's at degree 3. We have such a tree with 2 children on top of it. Since they are degree 1, there's a symmetrization on the tree, so that the tree, this tree is the same as minus the tree with ji. So there's a left and right on the blackboard, which I use. And this is the degree. And I can also count how many I have. So here, at degree 1, I have 3 of them. At degree 2, I have 2 of them. This is an antisymmetric 3 by 3 matrix, so I can have 3. And here it becomes more tricky. So let me see how far I thought of going. Let me just draw the degree 4 ones. So you can have 1 child and 1 parent here, for example, together. So this is, for example, degree 4. But I can also have 3 kids like this. And the question is, how many do we have now? So this can be 2 times 3, those give 6. And here, this is completely antisymmetric, so I get 7. So the dimension here of this number of generators is 7. And at degree 4, we get 18, and so on. So you see, this will be the numbers of the ghosts needed at each level, and this explodes. And that's our life. I will argue that actually this is slightly suboptimal. So one could put here 6 and 11. One calculates some cohomologies at each level, some procedure, which, however, is an infinite procedure, doesn't stop. You would need to calculate at each level a cohomology, which is not only difficult to calculate, it's an infinite step of them is needed to construct the number of ghosts. However, this construction is very, very easy. You just write all possible trees with these rules, and you find all the numbers which you get. And it will turn out that this addition of this additional tree here, for example, which gives us 7 instead of 6, has some very nice consequences, which I will say. So I still need to tell you how this delta prolongs to the other objects, and there are some kind of simple rules. So let's, for example, look at the delta of this one. So the 3 children being put together. I, J, K. So there's one operation which separates always. So the first operation in this delta is always put them apart. So this will give 3 trees. And you have to imagine that this is not all. There will come something else. You have to imagine that this is a forest, evidently, and you have to imagine that this is a symmetrized product. So this is a wedge product or whatever, a symmetrized, antisymmetric product of the 3 ghosts. So it's a cubic term in the ghosts. And then we know somehow that delta on these leaves, they give Li, so this will be also 3 terms. There's just some sign which I will look up here. So it's minus, and then if you put Li, then this leaf will disappear, because this is a coefficient in the ring which you can put just in front of the generators. These are the generators. We multiply afterwards everything by polynomials on R6. So this gives this space which we have, and Li is inside. And we have here now this tree, JK, plus the one from the middle, Lj, and so on. Minus Lk, let's make it black. And this is Ij. So these are the ghosts of degree 3. So this is linear in the ghosts, and that is cubic in ghosts of degree 1. Okay. And since the future, I see. Oh, I see. Since the future is makes everything equal, this delta should square to 0. Unfortunately, I'm not able. I wanted to show you just 5 minutes left. I wanted to show you what happens with a tree if, like, the husband has a girlfriend, and it's also kind of funny what happens there. But let me try to use the emergency program then. So there's this delta, but then there's also some homotopy, which we can introduce, which is extremely simple. So you look at a forest of these trees, and the homotopy just puts them in together one tree. So you have all these trees. For example, the homotopy of this would make just this out of it. And of a single tree, it just puts it to 0. So for example, if I have H delta acting on this, I just reproduce this tree. And if I have delta H, it's 0. It's got a single tree. And you see that H delta plus delta H on this is just the identity map. So it turns out that if I define such an H, so which takes several trees, I will just make it faster now. So whatever, like say this one, it would be just making it together into one tree. So you take the first tree, you take the second tree, and you make a new tree out of it. Okay, so that is H. And what one can prove is the following theorem. Which we have with Sasha and Chapuk, Camille Laurent-Jongu, which has two parts, namely, if I look at the forest of such Christmas trees, so S dot of epsilon dot, where epsilon dot is now the O module of these Christmas trees. So this is, I just multiply each of them with polynomials in an arbitrary way, and then I take a graded tensor product, which means I can have a forest of these Christmas trees. Together with this delta is a resolution of O divided by the ideal of the Li. So this corresponds to the previous picture, just to setting you the constraint surface. Okay, to get rid also of the flow of the constraints, you need to double this construction and to introduce the real ghosts. So these are the anti-ghosts, so they are no ghosts, they are real. And for that, you look at, for each tree, you introduce one shadow, like an antiparticle. So What are the ghosts? So these are the anti-ghosts. So this was these pi's in the previous notation of the introduction. Here the ghosts, which are these etas. And for each tree, let's take, for example, this one. You get a ghost tree. Same labels. And the opposite degree. But then the convention is actually in this BFV business to change the degrees here. So this is, okay, this is then the anti-ghost, then it's correct, anti-ghost degree or number, but then the total degree is the ghost number minus the anti-ghost number. So then this becomes -1, -2, -3, and should be flipped on the board going in the other direction. And this has a ghost degree or degree of, for example, +3 now, whereas this has -3. Okay. The next thing you do is 1 minute. Okay, very good. You introduce a Poisson bracket. Maybe you have the one with x and p, and they are conjugate to each other. And then you say that each tree is conjugate to this ghost tree. So you have this Poisson bracket there. And then the very nice thing that happens is you can construct. So I forgot in the theorem, there's a second part. So here is that in S dot epsilon dot of degree k bigger or equal to 2 of this anti-ghost degree, one has h delta plus delta h is the identity. So there's this homotopy. And now if you construct the BFV charge and the BFV Hamiltonian, the first terms you need to construct by hand up to degree 2 in this ghost momenta, but then you can write the recursive formula. And do you still have time to write the Q or maybe the H? One of them, right? I see it the same way. Yeah, let me write the H for the. So there's some story to come, which certainly on transparencies all would have been written, but I prefer to give a talk like this. It's a bit more lively. And so for H equal to a half p vector squared, you get the classical Hamiltonian to start with. Then you get minus 1 ghost contribution and 1 anti-ghost contribution, which are red. It's red. No, it seems green too. I may have eaten it. No, they're not here. Is this one? Yes, thank you. Okay, so here is the mother is the ghost here, and the father is the real person. But usually it's more the other way around, but okay. Then, so this is of anti-ghost degree 2, as you can see. There's no contributions anti-ghost degree 1. And the next contribution I still want to write, it starts with anti-ghost field 4. So you get one tree like this, where you have one child and one parent. And you need a ghost also to saturate this index I. And there it is the other way around. So here's the woman again, the mother again in the ghost sector. And you can ask about gender equality here, and I will just make a short remark about this at the very end. That is an anti-ghost of degree 4. And there are 3 more contributions. I write just the first of them. I write just the first of them. So we have 2 women and here is 1 couple, happy couple. And there are 3 more such terms, which I'm not going to write, and all of them are of degree 4, as you can see. And the last remark about gender equality, if you now add, if you make this into a harmonic oscillator, so if you have plus a half x vector square, then you get the corresponding additional contributions by just flipping man and woman, and everything is plus there. It's a better world. Okay, thank you.
Okay, thank you very much for this colorful talk. So time for some not so long questions. Yeah, look at this.
Okay, thank you for this nice talk. My question is the following. So on the forests, there is a co-product. There's basically all possible ways to chop up trees. And I was just wondering if you were using this in the definition of the delta, or if you were using the Hopf algebra structure later.
The rules are as follows roughly. If you have a complicated tree, like say any such a tree, one operation delta does is take away the root, and the other one like each contribution where 2 vertices coincide, so all possible options with signs. So in some sense, one operation is just eats 1 vertex. First part makes a forest, the other one leave 1 tree, and they can get no, it's like this. And then there's one part which acts on the leaves, so which makes what I wrote in the beginning, so the LIs and so on. Then there are some exceptions precisely with the ghost of degree 1. And then there's one additional thing, which you call molecules. So if you have a subtree of this, then there's a more complicated object entering delta, which is a map you need to construct. We know it exists, and we constructed it explicitly in this example of angular momentum. I should say that the whole construction works for arbitrary finitely generated ideals, and then you have more such exceptions. But then delta acting on this it has an extra contribution from this map, and it's needed to have the whole thing squared to 0. You're certainly thinking about this, but there's one thing like in this delta, which is actually something which is not canonical. Okay, which here we just constructed. So we just wrote what is delta of this, we write it down in the angular momentum, and there it is, delta squares to 0. But yeah, so there's this extra thing which is there.
Okay, so I would just to postpone further questions to the coffee break, and let's move on with our next speaker. We just disappear. Anyway, we have to. Speaker again. Sorry. Beamer or?
Yes. I'm a thief. So.
Okay, thank you. Christmas is over. Okay, hopefully it works. Okay,
Great,
good.
looks good. So our next speaker is Evgeny Skvortsov, and he will talk about strong homotopy algebras in conformal field theory and higher spin gravity.
Yes, right. Where's this device to flip slides? But I can also. Okay. Yes, good. And is light. Yes, okay. Thank you very much for having me here. It's really glad to be, because I think one of the distinctive feature of this series of conferences is that you can well, express ideas and pursue directions that are not super fashionable, mainstream, and slightly controversial. So accordingly, my main message of this talk is that higher spin symmetry is new Virasora. And when I said this in front of 2D CFT people, they just call security. So I didn't have time to take back and say that I'm not suggesting to replace Virasora by higher spin symmetry. No, not at all. They have non-overlapping domains of application. So Virasora is very famous in 2 dimensions, but my story is about 3-dimensional conformal field theories. These are almost textbook theories, which are called vector models. So this is something like phi to the 4th, but in 3 dimensions and tuned to criticality. So you're at fixed point where you have conformal symmetry. And the recent excitement about these models, especially those decorated with some Chern-Simons interaction, is due to the fact that people discovered or conjectured lots of new interesting dualities in these models, in particular 3-dimensional bosonization duality. But as a matter of fact, if you look at the spectrum of operators in these models, you find a lot of almost conserved tensors. So if they are conserved, we sort of know what to do. That's the usual symmetry, but they're not conserved a little bit and in a very special way. So this was dubbed slightly broken higher spin symmetry by Mondesen and Zhiboyedov, and it was not even clear what kind of mathematical structure that corresponds to. And my message is that this new type of symmetry can be well explained by quite old mathematical structure known as L infinity. And in fact, in this particular case, if you look very deep into this specific L infinity algebra, what you find is a fuzzy sphere. And so actually, mathematically, main statements we proved are about fuzzy sphere. And in particular, I will show you how one can prove this 3-dimensional bosonization duality, at least in the large n limit. And there is also holographic part of this story, but I guess we can skip that for the benefit of everyone if there is no. Then the first slide is a kind of propaganda about symmetries. So I think 99% of all symmetries are well taken care of by just Lie groups, Lie algebras. And maybe the best way to define a group is to think of transformations of something and try to eliminate any information about what it acts on. This is how you get all the axioms of the group. Well, okay, and then we have representations where this group acts. So then another type of asymmetry, which is, well, I think far less popular, is Youngian, just to give an example, where the structure is deformation of universal enveloping algebra as a Hopf algebra. And then it finds lots of applications in integrable models, spin chain. So another kind of higher structure that you would think is associated with symmetry are strong homotopy algebras. So there are some extensions of which usual Lie algebras and associative algebra are just particular examples. And whenever you have some square root of 0, some operator Q that squares to 0, you can interpret it as L infinity algebra, and then it finds lots of like systematizing and organizing applications in BV, Beresty, string field theory, also high spin gravity. So maybe Branislav will tell us about this later. And so the new part is related to the slightly broken higher spin symmetry that is thanks to having a lot of almost conserved tensor currents. And in this particular situation, so the mathematical structure is this L infinity, and I think well, particular example of L infinity, and I think that's maybe the first occurrence of L infinity as actual physical symmetry, because usually it plays a lot of role, but it doesn't act on physical operators. So here it does. And so the way you can think about what it does to you is that it gets, well, the symmetry gets entangled with its representation. So they form one big block. I'll give definition later that deforms and This is what explains all of these interesting features of 3 dimensions. So the plan is to say a few words about what higher spin symmetry is, then define Chern-Simons vector models and Bosonization duality, what this conjecture is about, and then try to argue how L infinity can explain all of that. And at the core of this result is fuzzy sphere, and which forms a nice story in its own. And yeah, higher spin grades, probably I'll have no time to say anything about. Okay, first, higher spin symmetry. So I'm sure you know what that is, but just under different names or no names. To give a very simple example where you can easily check or at least trust all the statements, I take just a free scalar or free Fermi in 3 dimensions, but okay, it can be done in any dimension. So then it's well known that in these theories, you can of course construct stress tensor, but on top of stress tensor, there are infinitely many of higher spin conserved tensors that you can construct just by inserting more derivatives and fixing coefficients in such a way that they are conserved. So then conserved quantities should be somehow responsible for some symmetries. And at least for stress tensor, we know how to do that, but tensor is not a current. So you need to kill one index here, which is done by constructing a stress tensor with a conformal killing vector so that you form a current. And conformal killing vector has as many free parameters inside as the dimension of conformal algebra. So you have as many charges as the dimension of conformal algebra, which explains why CFT is called CFT, not because it has stress tensor, but because you have all these charges that form conformal algebra. So now the question, what are these higher spin currents responsible for? And we've seen that at least in 3 theories, you can easily construct these higher spin tensors, but what about the opposite statement? Can you imagine some conformal field theory in dimension 3 or greater with a stress tensor, that's normal, and with at least one higher spin current, which is a bit abnormal? And in fact, the statement is that, assuming this, you can show that in this conformal field theory, you in fact have higher spin currents of all spins, and correlation functions of those look like in some of the 3 conformal field theories. So essentially, in dimension 3 or greater, having higher spin current means that your CFT is a free one, and you have infinitely many of these. So any symmetry is certainly useful unless too much. So in this case, higher spin symmetry is way too much because only 3 conformal field theories survive so many symmetries. Okay, if we proceed the usual logic, like we have conserved tensor, we should construct current, then we have charge, then we can have a look at our symmetry algebra. Then it's easy to see, of course, that if you have a conserved tensor, you need to kill all but one index, which you can do with some generalization of conformal killing vector called killing tensor. And this way you get lots of conserved currents. They're parameterized by these killing tensors. And this way you also get a lot of conserved charges. But there is something special called miracle 1 that happens for these higher spin currents. So we know that if you have a charge, you can commute the charge and get, well, probably another charge. So they form some Lie algebra. But what's special here is that, in fact, this Lie algebra originates from some associative algebra. So in fact, the structure is stronger. And the simplest way to understand this is just to look at the equations of motion, say this Klein-Gordon equation. We know it's conformally invariant. And in practice, it means that there is some specific transformation parameterized by conformal killing vector so that solutions are mapped to solutions. But since the equation is a linear one, you don't have to take commutator of your symmetries to get a symmetry. You can just multiply them in an associative way. So this way you generate some high derivative symmetries, which are called higher symmetries or higher spin symmetries. So in particular, something like this hypertranslation is a part of this algebra. So obviously you get something infinite dimensional, associative, but still containing your conformal algebra as a Lie subalgebra. And slightly different way to explain the same thing is, again, start thinking about scalar field. Say it's jet space, which is this wedge, or just Taylor coefficients. And then equations of motion, they single out some sub-wedge here, this space of solutions. And by definition, symmetries are transformations that map solutions to solutions. So if you think about the space of solution just as a vector space, then all matrices that map this vector space to itself are symmetries. And then it just has some additional structure of having a conformal algebra inside. So in some sense, conformal algebra is just matrices in this vector space. You can also understand this as deformation quantization of the corresponding coadjoint orbit, which explains everything, like why it's infinite dimensional, why it's related to some free field, and why conformal algebra is inside. And remembering that high spin currents are bilinear in these fundamental fields, there is another miracle that, while currents being in the tensor product of V with V, they're almost isomorphic to high spin algebra, which are maps from V to V. So this plays some special role later, but you need to learn how to map bra to ket, and okay, that's done with inversion map. And to be even more specific, so in 3 dimensions, this high spin symmetries, and in particular the vector space of solution, was understood in a very simple way by Dirac. As a representation of conformal algebra, the space of solutions of Klein-Gordon and Dirac equations are just even and odd vectors in the Fock space of 2-dimensional harmonic oscillator. Of course, this relies on some special isomorphism that takes place in 3 dimensions. And then it's very easy to say what this high spin algebra is. It's just the algebra of all operators A and A dagger. So you take any of these, obviously it maps space to itself. And of course, it has a very nice representation as just a deformation quantization. So you can use Moyle-Weil star product to take the product of 2 elements in the high spin algebra. So this is just the simplest realization of this idea. So what? P and Q. Well, it's just instead of A dagger, you can use P and Q, which looks a bit more natural when you think of star product. But of course, you can write star product in terms of A dagger. Just notation-wise, it looks a bit ugly. Yeah, exactly. Yes. So that's the same Moyle-Weil star product that people use in non-commutative field theory, but okay, here just plays slightly different role. So, okay, we have tensors, currents, we have some infinite symmetry. What about invariance as or correlation functions as invariance of this symmetry? So we know that the usual conformal symmetry, it's not powerful enough to fix correlation functions. It imposes certain constraints, but they are too weak, so you have to work hard to fix them by some other principles. So is high spin symmetry powerful enough to fix correlators? Well, one of the definitions I gave was in terms of matrices that map solution space to itself. So you shouldn't be too surprised to hear that high spin algebra is equipped with trace, which is sort of the usual matrix trace. So it's very easy to construct invariants, which are this trace of something. And of course, invariants don't know what you want to compute, but if you choose these elements wisely at certain coherent states that represent these high spin currents, then you indeed find expressions for the correlation functions in these theories. And this trace formula makes not only conformal symmetry, but full high spin symmetry manifest. And well, it's easy to say, but one can also compute them. So I'm not going into details, but say 4-point functions. It's not just one 4-point function. It's a generating function of all 4-point functions. Looks like some trigonometric function of certain conformal invariant tensor structures that are standard in this literature, but it's not important now what they are. Some simple functions of coordinates. Okay, so let me summarize this high spin part. So in every free conformal field theory, we have infinitely many of high spin conserved tensors. They generate some charges that form an infinite dimensional algebra that extends conformal algebra. So this way, high spin algebra looks a bit like Virasoro, being an infinite dimensional extension of global conformal symmetry. So we well, the way you construct it using this recipe, it's a Lie algebra. And then the miracle one that I'll try to explain is that, in fact, this Lie algebra comes from associative algebra. It's not always the case. Say, I don't know, GLN is both Lie algebra and associative algebra, but E8 is not commutator of matrices and some associative algebra of the same size. So here something special happens, that this Lie algebra in fact comes from associative algebra, which can be explained through deformation quantization. So in a sense, free CFT is equivalent to having this associative algebra that we call higher spin algebra, and higher spin algebra knows everything. In particular, it knows all your correlation functions, which are unique invariants of these algebras. And a couple of other interesting facts is that this multiplet of higher spin currents form just one irreducible representation of this higher spin algebra, and the fundamental field you started with also is an irreducible representation. And what's important for later is that only in 3 dimensions, higher spin algebra constructed from free scalar and free fermion are actually the same. This is this Weil algebra of functions of AA dagger, or you can think of this as a Moyle-Weil star product algebra. And one can also show that these traces are unique invariants of this algebra. So there are no other invariants that can play a role of correlation functions. Good. So now let me explain how we can use this technology to say something interesting about Chern-Simons meta theories. So what's nice about these theories is that they actually describe physics, but not in the sense of fundamental interactions, but in the sense of condensed matter. They cover all or almost all second-order phase transitions that take place in 3 dimensions, like Ising model or this hyperfluid transition. So there is a whole zoo of Chern-Simons meta theories, but I will need just, well, for simplicity, I will give you the 4 simplest theories of this kind. So we can take free scalar or free fermion and also interacting scalar with just 5 to the 4th interaction, but tuned to criticality so that you have a conformal field here. And likewise, well, it's usually called Ising or Wilson-Fisher conformal point. And likewise for fermion, you can add a certain interaction, and then it's called Gross-Neveu model. Now, yes, just let me say exactly. Yes, let me just repeat what Thomas said. That was exactly the words I was going to say. So I take all of these guys in some vector representation of some group like UN, and then I would like to gauge this symmetry. So I covariantize derivative, and to make story even better, I can use the luxury available in 3 dimensions of adding Chern-Simons term here. So indeed, now what was free is not free anymore because you have an interaction with Chern-Simons field. And this way you have 4 theories, 2 of them based on bosonic matter, 2 of them based on fermionic matter. All of them are interacting. They describe lots of physics, break parity in general. And you have 2 parameters here, number of fields, which is n. And at least in the large n limit, Chern-Simons level can be combined with n to an almost continuous coupling, which is analog of 't Hooft coupling in gauge theories. And now, what is the conjecture of 3-dimensional bosonization duality? Remember the color: blue bosonic and red fermionic. So the conjecture is that these 4 theories coincide pairwise. So in the sense that if you couple this Wilson-Fisher to Chern-Simons, you have 1 parameter family of conformal field theories parameterized by this lambda. And you take free fermion and couple it to Chern-Simons, so it's not free anymore. You have likewise a 1 parameter family of conformal field theories, and the conjecture that these are actually the same theories. So everything you compute in those correlation functions, anomalous dimensions, must be the same, provided you identify parameters on both sides of the duality appropriately. And likewise here. So 4 theories must coincide pairwise. And in these theories, the simplest gauge invariant operators to look at are exactly higher spin tensors. They're no longer conserved, of course, because these theories are not free. So if you want to check duality or prove duality, the simplest thing to look at are higher spin tensors. In principle, they know everything about everything as well. So what happens with this higher spin current? Of course, they cannot be conserved because you already have this statement that if you have a conserved higher spin tensor, then you see if T is a free one, so it's not very interesting. However, these vector models are very special in having very few operators in the spectrum. So there is almost nothing you can put on the right-hand side of non-conservation equation, because if current is not conserved, on the right-hand side you have to have something. This has to be an operator, and there are very few operators to put there. So in particular, if you just count spin, conformal dimension, the only thing to write would be something bilinear in the higher spin tensors themselves. And this is exactly, well, the key feature here, because if you just have a current in some theory and it's not conserved, and what stays on the right-hand side is some other random operator, there is probably nothing interesting you can learn. Your symmetry is just broken, forget about it. But here, the non-conservation is driven by the currents themselves. So they are responsible for their own non-conservation. And this picture explains how you can put it to practical use. So that's a man, probably most of you know, who is trying to pull himself out of a swamp by his own hair. So this is the idea of bootstrap. And indeed, people checked many things just by using this non-conservation law inside correlation functions. But it's not quite clear what's the right mathematical structure behind, because as long as currents are not conserved, you lost conservation of charges, you lost your algebra, and so on. So let me just recall what happens when higher spin symmetry is there. So you have conserved tensors, they generate charges, charges form some algebra, and higher spin currents form representation of that algebra. So you have this kind of bilinear maps. So first of all, bracket between two elements in the higher spin algebra, and also action of an element from the higher spin algebra on higher spin current. But what happens in these vector models is that currents are not conserved. Accordingly, charges, they just don't map currents to the currents themselves. There are some corrections. And what is the right math to accommodate such a structure? And if you look at these formulas carefully, then it should be clear that you can just isolate higher spin algebra or currents and say try to deform higher spin algebra. It's not even possible. So what you should do is to deform the algebra together with its action on this module that higher spin algebra, higher spin currents form. And the right structure to accommodate all of that is L infinity. In this L infinity, you just have two degrees, one corresponding to higher spin algebra and another corresponding to currents, so that you can deform your action accordingly. And also you have to make sure that commutator of two transformations give you transformation of the same kind, which now on top of the bracket in the higher spin algebra can have some additional terms here. So that's an L infinity algebra. And well, just recall what infinity is. And in this particular case, we have some graded space. In this case, it has 2 degrees. There are lots of multilinear maps. They satisfy some kind of Jacobi identity. So now we need to construct this L infinity and say something about it to attack the 3-dimensional bosonization duality. So I'm skipping lots of details, but this particular L infinity algebra we're after originates from A infinity, which again, I'm not going to define. But very deep inside this A infinity algebra, there is a specific deformation of higher spin algebra, which is just fuzzy sphere. And that's an interesting story on its own, because many people did all this work in the past. And it started with Wegener, who took canonical commutation relations, some simple Hamiltonian, which was in his case just harmonic oscillator, and we know that there are some quantum equations of motion which are sort of true because we confirmed this in experiment. And then he asked the opposite question. Okay, quantum equations of motion being related to experiments are more important than canonical commutation relations. But do quantum equations of motion imply canonical commutation relations? And the result is that no, there is one additional parameter that you can insert into canonical commutation relations. There's a usual H bar, and there is this nu that comes with R, which is an operator that realizes just reflection symmetry. So it flips the sign of Q and P. So this is one additional parameter ambiguity here. And this algebra, which is known since Wegener, is closely related to non-commutative sphere and was studied many times. in the literature. So but you can also ask what's the relation between these and deformation quantization program, because in deformation quantization you're given some Poisson manifold. In this case it's even symplectic, you can quantize, but then this way you get one parameter, which is h bar. So where this additional freedom in canonical commutation relation is coming from? So the answer is that it comes from orbifold. So you need to know how to quantize not manifold but orbifold, and in fact this leads to additional parameters, and this story is not finished yet because there is no analog of Kontsevich or Fedosov deformation quantization that solves this for arbitrary orbifolds. But in this particular case, people know how to do that just by hand. So, okay, so we need to study this fuzzy sphere algebra and make some statements about it. So first, necessary for bosonization statement was made by Dirac that I already explained, that higher spin algebra based on free boson and free fermion are in fact isomorphic. That's the necessary condition for this three-dimensional bosonization have chance to happen. So then we also know that there is exactly one invariant here to serve as endpoint correlation function, and we can even compute it and get the right answer. So now if you construct L infinity, and here I'm skipping lots of steps because I'm not explaining how exactly this deformation here is related to this many multilinear maps of L infinity that you have to construct, but you can construct that. So then as a result, you can find that this L infinity depends on two additional parameters that are not here in the free limit. So this additional for us, just phenomenological parameters, of course, should be related to these microscopical parameters of Chern-Simons meta theories. Then you can also analyze some cohomology of this algebra, which again boils down to cohomology of fuzzy sphere, and find that these invariants can be deformed so that they remain invariants under this L infinity algebra. And in fact, the generating function has a very simple form, which is reminiscent of one loop exact result. There's some trace log, but the product here is exactly the one of fuzzy sphere that deforms the Moyle-Weil star product along this reflection direction. And then, well, that's very general statement, but again, invariants don't know what you really want to compute. But there is a simple consequence that well can be checked and with examples and requires zero calculation. Just from this formula, you can easily see that endpoint functions they have to have this form. So you have a finite number of certain fixed conformal invariant structures times some parameters. This is quite special because usually correlation functions can depend in highly non-trivial way on coupling constants, but this is not the case here. And in fact, it agrees with all studies of correlation functions in these models. Yes, so we can also show that these invariants are unique. They can be deformed, which implies a three-dimensional bosonization because we could fix. Thank you. We could fix correlation functions just from the symmetry. So we never asked the question what these higher spin currents are built from, whether these are fermions or bosons. Symmetry already fixes, so you can have not 2 but 100 different microscopical realization of the same idea. Correlation functions are just fixed by symmetry, which implies three-dimensional bosonization in this case. And then maybe I'll say a few words, but really briefly, about higher spin gravity. I maybe refer to talk by Tung later today. So the context here is that as long as you have some conformal field theory, in this case Chern-Simons meta theories, you can ask, well, you can turn on edges CFT and ask what's the gravitational dual of those theories has to be. And quite from the general edges CFT dictionary, you know that something conserved is dual to something gauge. So if you have a conserved stress tensor, then it's dual to spin 2 massless field, that is graviton. And so not surprisingly, higher spin conserved tensors are dual to massless higher spin fields in eddies. But in general, theories of this type are very difficult to construct because they don't want to exist, or just too non-local in the sense that there are many of these theories we expect to exist, but they're too non-local, so some of the non-localities are not tamed yet. But there are nice exemptions. In particular, the talk later that is based on this higher spin IKKT model, and chiral higher spin gravity. Just in a few words, what that is? It's the most minimal higher spin theory you can construct, but still its spectrum is infinite. So it has fields of all spins. You can show it's one loop, at least one loop UV finite, and so on. Has many nice properties. So, but what's the place of this theory here? So this theory has the right spectrum to be dual to Chern-Simons meta theories, and it's also a theory in ADS4, so that you need for ADS CFT to apply. But it's too small, not in the sense of spectrum, but in the sense of interaction. So say already at the cubic level, you can see that all interactions are covered by what we call chiral and anti-chiral. So we sort of have half of the theory here. So nevertheless, its very existence also supports this three-dimensional bosonization duality, and you can make specific predictions for correlation functions and so on. And again, if you attack bosonization duality through higher spin gravity, bosonization is manifest because higher spin fields are dual to currents, and again they're completely insensitive to what kind of matter these currents are built from. So if you can make some general statements regarding correlation functions from higher spin gravity, then you prove in duality because it will be true for all models of this type. But what I'm going to do now is try to tell you a bit more about this L infinity algebra. I'll try to sell exactly the same L infinity algebra twice, now as a field theory. And the way to do that is to consider a sigma model, because remember that if you have L infinity algebra, you can just pack it into a Q and into an odd vector field that squares to 0. So you have some super manifold equipped with this homological vector field. So you can consider sigma model from our space-time to this super manifold and write equations of this form with the same Q that originates from L infinity algebra that I have not quite presented the details of. Okay, so you can ask, well, how general that is. And in fact, any field theory or any PDE can be cast into such a form. And there are many names in physics and mathematics for that, for example, IKZ. And this is the final result. So let me just make a general comment that usually, so even though anything, for example, Einstein gravity, can be written in this way, for field theories, this Q manifold has to be infinite dimensional. So going back to conformal field theory, the space of higher spin currents and descendants is infinite dimensional. Higher spin algebra itself is infinite dimensional. So the vector space underlying this L infinity is infinite dimensional. And for infinite dimensional Q manifold, there is a problem that if you just perform some change of coordinates, you think it's a change of coordinates from a field theory point of view, most likely it will correspond to some highly non-local field redefinition that completely destroys equivalence theorem and so on. So you should be super careful. And we've been super careful. And this is the final result, which I'm going to present. So suppose we want to write all these multilinear maps, and we have two arguments here from higher spin algebra and lots of these higher spin currents. So if you know Kontsevich formality, then there are this, well, especially it's a Poisson sigma model representation, thanks to people who first created Poisson sigma model and then quantized. So you know that there are some graphs which are Feynman diagrams of this Poisson sigma model. So in our case, because we started from Moyle-Weil algebra, well, the Poisson structure is symplectic, constant, so it's very boring. And then out of these Feynman graphs, nothing survives in the bulk. Interesting. So you have some points in the bulk, but they immediately hit points in the boundary that correspond to arguments here. So now the miracle is that all these graphs somehow exponentiate, but there is some modular left. And this modular correspond to, as a configuration space, to the space of convex polygons, or we actually like this complementary picture, which we call swallowtails, these guys. And then some weak contractions here between two higher spin algebra elements, they have as a coefficient the area of the swallowtail, and contractions between higher spin algebra and higher spin current, they have coordinates x and y of these vectors. And then you have to integrate over this configuration space. So in fact, this algebra that we constructed it's a pre-Calabi-Yau algebra, and quite strangely, Kontsevich and collaborators have been studying this this in previous years. So it's quite a special type of A-infinity algebra. And the question I'm asking, I'm begging all topological field theory experts to tell me if there is a model for which, well, as a very degenerate result, you have this kind of configuration space of convex polygons, which is, of course, also related to Grassmannian. So I think I should conclude, which I'm doing. So, okay, I hope I convinced you that higher spin symmetry is new, but with a different domain of application, Virasora. So it works in 3 dimensions. And uniqueness of this, well, but the right way to understand it is to deform it into slightly broken symmetry, which should be understood as L-infinity algebra. Uniqueness of invariance of this algebra implies 3-dimensional Bosonization duality. But again, on a kind of propaganda side, so this is a new type of physical symmetry where transformations, algebra, and the object, the tecton module, deform together. And well, that's the same as the algebra it already mentioned in the previous talk. So now a bit more propaganda. So if so what we did was in the large n limit. But if you look in the opposite limit, like the very small n limit, n1, which is Ising model itself, then the dimension of the very first higher spin current is tiny. It's already like 2%, sort of, and dimensions decay as spin increases. So higher spin symmetry seems to be present even in this example, but yeah, so it would be nice to explore that. So then the chiral higher spin gravity is dual to a closed subsector of Chern-Simons vector models, but nobody knows yet how to find it because Lagrangian of Chern-Simons vector theories is not suitable for that. And then we constructed the maps of this L-infinity algebra explicitly, and somehow the first 2 maps, they just originate from Kontsevich or its extension known as Scheuche-Ziegen-Kontsevich formality, but other maps, we don't know where they're coming from. We just constructed them by hand, and we're quite lucky to do that. So it would be nice to identify at least topological field theory that gives this configuration space that we have here. And it's also clear that these are just 2 layers of some big formality that we have no idea what it is. And if you want to read more about this stuff and other higher spins, then we have Snowmass paper this year, which is short, nice reading that I just advertise using this opportunity. So thank you very much for your attention. May the higher spin symmetry be with you.
Thank you. Thank you very much, and also for staying in time. So, time for some questions. Yeah, please.
Microphone, probably.
It was very good talk. I have 2 questions. One question is that in the higher spin theory, as you know, Misha Vasiliev was a kind of master. Yeah. So what you did important, which is going outside of his framework. Yeah. Or this is just another way of describing his approach.
Well,
or you have an essential new elements. I mean, which
yeah, we have some elements. So first of all, this application of higher spin symmetries on CFT side, it's kind of out of business. Secondly, we have some important corrections to higher spin gravities, because the theories that he tried to construct, they're exactly the ones I call untamed. So they are too non-local, so we still don't know how to work with them. So there are some severe non-localities, so you can't extract any physical consequences from these theories. But we have another theory, which we call chiral. So it's completely new, nice, local, and okay, it's at least 1 loop UV finite and so on. So we hope to get actually what people promised us 40 years ago to get out of higher spin gravities now, because we have a nice theory where you can actually do calculations. And another example would be this IKKT-based model that you will hear talk later today, which are not completely unrelated, in fact, right?
Yeah, in Vasiliev papers, there are these slightly broken symmetry terms, which you have here. He has, or you wouldn't have,
well,
he doesn't have.
So he is using the same strong homotopy algebra technology to construct field theory. Yeah. And then as a field theory, it's too non-local. So so that's exactly the issue I mentioned. So if you're not in the right coordinates in this L infinity algebra, what you find is just meaningless interactions. And that's exactly the case. So the technology is the same, but we have a theory that actually works. And we have applications on safety side. That's a completely different news story.
And second short question, if you go from d equals 3 to d equals 4, I mean, of course, you lose all this advantage of Chern-Simons, but can you do it?
We can do it to some extent, in the sense that, no, probably we cannot, because phi to the fourth theory is trivial or believed to be trivial in 4 dimensions. So vector models in 4 dimensions, I don't think there are good examples actually of those, but one can do similar things in 5 dimensions. There is again, non-trivial vector models, but yes, you do lose Chern-Simons, which, as you see, was important here. It's only because of this Chern-Simons interaction you can actually start from something that is Ising model and end up in something that looks like Fermion. So that was very special to 3 dimensions. So I think some of these steps can be done in high dimensions like 5, but they're not maybe as exciting because there is no 3-dimensional or 5-dimensional Booleanization duality and things like that. But there are vector models in which, would be nice to get some new techniques to perform calculations.
With the Penrose way of looking at gravity.
Well, but this theory that I just said a few words about, the chiral one, it is in 4 dimensions, and it is in fact closely related to twistors. So this is what we study now, and probably Toon will say that, but it looks like it's very natural theory on twistor space, like Chern-Simons theory on twistor space. Yeah, so twistors are a completely appropriate tool, but I didn't mention this at all. Yes.
I'll ask 2 or 3 questions related. First is notation. L infinity, there is nothing to do with what happens in Banach spaces, where LP, when P goes to infinity, you have L infinity of boundary sequences. That what I'm trying to understand the notation. Okay? First question. Second question is you had a module on which is that a Hilbert space? So related question is, if it is, what happens to the Coleman-Mandula theorem? There is no scattering in these models.
Okay, so these are all good questions. Maybe regarding notation.
And finally, one more question.
Yes.
Is there a quantum field theory for this? Where is for higher spins here?
Yes.
Is there an actual local quantum field theory?
Okay. That's okay. I try to remember all your questions. Yes. First of all, I was thinking about designing some LaTeX package that covers out this corner because we have okay. So maybe notation. I don't quite understand the question. So L infinity is just a graded vector space equipped with some multilinear. Okay. You want the norm here.
And there is one space which is called L infinity.
No, these are different things. I mean, L infinity algebra, I think, has nothing to do with any.
Yeah, it's not an algebra. It is a Banach space. It's a norm.
No, there is no norm in these axioms. So you don't need it. Yeah, but okay, if you agree that Lie algebras exist and they don't require norm, then this is just graded extension where you have brackets with more arguments. So it's at the same level of definition, of rigorous definition as you have for Lie algebras, just a bit more of this brackets and graded space. So L infinity algebra is just natural generalization of Lie algebras that I could with multilinear brackets. Now let me try to remember your next question. So you said, well, if there is a Hilbert space and things like that. So yes, so these are actually one of the few conformal field, one of the few field theories where mathematicians prove their existence. This 3-dimensional phi to the fourth, I think, apart from free theories, I think that's one of the few where mathematicians actually proved their existence. So J's, these higher spin currents, these are operators. So they belong to your physical space, but we are not using this structure at all. So we're just using symmetries. So symmetries are good enough to fix correlation functions, and this is exactly what you observe in experiment. You don't observe Hilbert.
Have the correlated, and they are defining states on the algebra, one can make a GNS and get a Hilbert space.
Could, yes. Yeah. So we have not done any of this. So we're just using symmetry to fix correlation functions, and that's what you observe in experiment. But you're right, yes.
So we don't know what the Hilbert space is.
No, we never asked this question because you don't observe Hilbert space.
What happens to Coleman-Mandula?
Okay, yes, that's a good point. So what happens to Coleman-Mandula is that they want to assume there is some high symmetry that goes beyond, say, Poincare, or there is extension to conformal, and so on. And that's exactly what eliminates, well, how we avoid Coleman-Mandula, because it's not a Lie symmetry. There is no Lie algebra that extends conformal or Poincare that actually acts on your asymptotic states or correlation functions. So it's not a Lie algebra. So it immediately avoids, bypasses Coleman-Mandula theorem, like it never happened, because it's not a Lie symmetry.
So final question is there a quantum field theory which is broken?
Yes, right. Okay, so this is what we believe to be such a theory, but what rigorously has been proven. So you have a local field theory that has graviton and higher spin fields, and we could show by direct calculation that despite most of the interactions are non-renormalizable, at least at one loop you don't find any UV divergences. Somehow they miraculously cancel out. And then of course you need to push it to higher loops and so on. But okay, we believe that in fact with some twistor technology we can bypass this and have a. So yes, I believe it's a UV finite theory that incorporates graviton and massless high spin field, but it was shown up to one loop only.
Okay, so I suggest that we thank the speaker again.
Thank you.
And go for a coffee break. And let's reconvene at 10 before 12.
Give me a second. Oh, you sent one today? Yesterday. Give me the correction. They're actually using the projector right now. But yeah, I'm pretty sure I have a couple. I introduced some corrections and typos in the. Give me a second. I'm sorry. Excuse me. Can I just for a second? Can I use the screen? No. Yes, of course. 1 second. That's all.